Hey everyone, and welcome back to C++ Under the Microscope. Today we're doing a deep dive on a feature that every modern C++ developer uses, but few actually look under the hood. That's the lambda. We use them for std sort, for std for each, for callbacks. We love them because they're convenient, but what is a lambda really? Is it magic? Is it a function? Is it an object? By the end of this video, we're going to pop the hood, look at the assembly, and see that a lambda is just syntactic sugar. It's a lie that the compiler tells us to make our lives easier. The spoiler alert, they are zero-cost abstractions. I'm going to start with the absolute simplest, the most useless lambda in the world. A captureless, stateless lambda. It does nothing. And here's the compiled assembly. Okay, there is a lot of noise here, but this is the main function. And if we scroll here, we can see, look at that call instruction. This is our first clue. It's calling the function operator. That means lambda isn't a function, it's an object. It's a functor. Let me prove this to you. If a lambda is just an object with a function operator, we should be able to write what the compiler writes for us. It's just a struct with a const call operator. That's why we say lambdas are syntactic sugar for functors. One other way to check this is to use CPP Insights. This is a website that will strip all the syntactic sugar, and we can see this lambda is just a class with this operator, the function operator. And here we can see we create an instance of it and we call that operator here. Now let's turn on optimizations. This is where the magic happens. I'm going to change the compiler flags to O2 and look at the main. It's gone. The entire lambda call vanished. Now why? Because our lambda had no state. It was an empty struct and it did nothing. The compiler realized that calling an empty function or an empty object has no observable behavior, so it optimized the whole thing away. But more importantly, even if the lambda had body, there is no object, there is no call, the compiler just inlined the value. This is the zero-cost abstraction I mentioned. You get the readability of a lambda, but the performance of a hard-coded constant. Now let's return this to O0. Before we move on to stateful lambdas, I want to take a look at the mangled name. Now, if I add the second lambda, now we see the two calls to the function operator, and we can see the mangled names here. Even though they look the same to us, to the compiler, these are two different objects. They are unique syntactic structs, and for the compiler, there are different types. That's why you can't assign one lambda to another. For example, you can't do this. It will complain about the lack of overloaded equals. For the compiler, these two are different types. Now let's make it hold state. Let's capture a variable by value. In our mental model of the lambda, the compiler generated struct now needs to hold an integer. It looks something like this. It will look something like this. Now let's check the CPP Insights to actually see what it generates. And as you can see, this is a class, some compiler generated name, and here is the function operator, and we have int x and the constructor that stores that value to x. And again, we create an instance of that and we pass the value x here. And we call the operator. Now let's look at the assembly with O0. First, we store 10 into this address. Then we store the value that's already stored here to EIX. Then we make a copy. We can see that the value in EIX is stored at this location. And an integer is 4 bytes in x64, so we can count that. Here, RBB minus 4, that's 4 bytes. And RBB minus 8, that's 4 more bytes where we store the value 10. Then we see that the same address, again, we store whatever is here into AIX. Then RBB minus 12, or we add 4 more bytes and we store into that AIX. So we effectively copy the value 10 here as well. Then that's the LEA instruction. What it does is it takes the address of whatever is here and stores it into this register. And again, we can see the code to this operator, this function operator. So we can see in the assembly that the compiler is actually making a copy here. Now let's see what happens if we change this to O2 optimizations. And again, it's all gone. The compiler saw that x was constant and the lambda captured it, and it just propagated the constant directly to the return. The lambda object ceased to exist in the final binary. Now let's capture by reference, which is usually more common. Our mental model of the lambda changes. The struct now holds a pointer or a reference to the value x here. Now let's see that. This should be generally what the compiler will generate, but let's check it with CPP Insights. And again, the same story. We have the class, and yeah, it uses int reference. This is the constructor where it's initialized, and this is how the lambda is created and the operator, the function operator called. Now let's check the assembly. This is with O0. And a very similar story, we can see that the number 10 is stored at this address. But then watch what happens. We have this instruction, LEA, and we take the address that's here and we write it to REX. Then we move the value that's stored in REX, that's the address here, into RBP minus 16. Now, why minus 16? Because on x64, a pointer is 8 bytes. And we can count it again. First, we have 4 bytes and we store 0 here. Then we add 4 more bytes for the integer. An integer is 4 bytes. Then we write in RAX the address of this value here. And then we store that, and it's a pointer now. We store the value of the pointer itself into RBP minus 16. So we add 8 bytes, not 4. It's a pointer which takes 8 bytes. Then we write that to RDI and we call the function operator here. And if we use O2 as optimization, you can see it's all gone, the same story. Now let's check the sizes of these lambdas. We can see the size of the stateless lambda is 1 byte. The state of the stateful is 4 bytes. The stateless lambda has a size of 1 it's an empty struct. In C++, every object must have a unique address, so empty structs have size of 1. The stateful lambda has size of 4, and on x64, integer is 4 byte. So it literally holds the integer x inside of it. That's why it's 4. What if we capture by reference? This is where we can get into trouble with dangling pointers. Let's see the example. Let's look at the assembly. We see RDI, that will be the pointer to where this int ref x points to in memory. And we write that value to RBI minus 16. Then whatever it was written here, that pointer, we write that to REX register here, and then we copy the value of the pointer into this address here. So at that moment, we have the pointer to the original integer written into this location. Now, if that address points to a stack variable that goes out of scope, your lambda is now holding a pointer to a garbage value. That's the whole issue behind that. If it goes out of scope, if it's destroyed for some reason, we hold a garbage value. So let's recap what we learned under the microscope today. Lambdas are not functions. They are syntactic sugar for compiler-generated structs, functors. Stateless lambdas are empty structs. Calling them is just a normal function call with optimizations. They inline completely, so zero overhead. Stateful lambdas contain the captured variable as data members. Their size grows with what they capture. The compiler gives them unique mangled names because each lambda expression is a unique type. If you enjoyed this look under the hood, hit that like button and subscribe for more episodes of C++ Under the Microscope. Thanks for watching and keep coding.